All right, hey folks. So this week's going to be pretty exciting, this lecture, because what we're going to do is finally actually start doing statistics. I mean, we already have been, but now I think it'll start feeling like it. All right. And first, I want to kind of go over a small overview of what we're even trying to do when we do statistics. All right. So in general, we have something that we don't know, right? It could be anything, right? Something we don't know. And presumably we want to know about it, right? Now, this can, like I said, this could be truly anything that you could imagine. You know, it could be, did the Yankees win the 1952 World Series? The question, yes, did they or not, right? We don't, maybe you know the answer, I don't. It could be, how many COVID cases will there be in a week in the United States? It could be, how happy will I be? What were the odds of me getting divorced if I marry this person? Right? How happy will I be if I go on to try to get my PhD? Right? You can do any sort of thing, and that one, it's like, okay, so I don't know it. Now what? All right. Well, what you want to do is you want to somehow have data or information, bring in other information that you do know, and use that to try to help you figure out your answer. And as all statistics says, bring in data and information from outside to answer the question that you don't know, or at least give you some estimate as to the answer you don't know. Now, the first step of doing this is to take this thing that we don't know and somehow bring it into the world of math. So, for example, how happy will I be if I go for a PhD? You might ask, well, what does it mean to be happy? Like, how do you measure that? And that could be you can imagine something like uh, if somebody were to ask me on a scale from 1 to 10 how happy I was, what would I answer? Right? And now we've taken that and turned it into something that is measurable, right? So we have to be able to somehow measure the thing, or maybe not directly, but at least be able to put a number on it, right? Like did the Yankees win the World Series? Sure, the true answer is yes or no, but we could put it down at the very least some probability, which is how confident we are that they had won. Are we 80% confident they won? 20%? Right? Do we think that there's only 20% chance they had won? Etc. So we have to somehow take the question and boil it down to either like a number or a series of numbers. Was this type of educational intervention we tried doing, was it effective? Right? And so how do you measure that? Well, maybe you have to do a test to see how effective it was, and did it raise their test scores? Or you could ask them how they feel about, because you might have been wanting to make it so that way they're more motivated about learning. So you'd have to maybe do a quiz, not a quiz, but like a survey to see how they felt about it. Right? There's a lot of different things, but we have to turn it into a number. And then, so now that we know that, okay, we can somehow, there's some parameter that we're interested in. Specifically, we want to turn this into a set of parameters that we're interested in. We're interested in. And now, once again, this parameter could be something that's kind of a made up concept. For example, what's the slope of a line of a linear regression, right? And it's like, well, the thing isn't actually linear, but sure, we can give you some slope for it. We'll talk about that a little bit later. It might not actually be some physical concept, but rather more of a epistemological made up idea. But as long as it's a number that we can at least try to estimate, well, okay. As long as it has meaning to us. So we have some parameters that we're interested in from our original question. And now what we need to do, once we've done this, is figure out how do we bring in all this other information that we do know, that we do have, and how do we incorporate that to actually get some estimate to these parameters that we're interested in, right? And that's the basic goal. And so the idea of it is that first we kind of the first step is to kind of explore our question, explore and develop the question, the question. The next thing is to model, to build a model. And when you build the model, what you're doing is that this model that we're talking about is the thing that says, okay, first of all, what are the parameters that we're interested in from our question? And then also, how do we describe how the other uh, data, all the other information we have, comes into play, right? How are they involved with the parameters that we're interested in? Because it's possible that, okay, what's the probability that the Yankees won the World Series in 1952? And maybe, hey, here's some information I have. I had soup for dinner. It's like, okay, well, that information doesn't really relate at all to the question at hand, so it's kind of worthless information. So you have to somehow have, when you do have relevant information, like, okay, how many World Series did the Yankees win, during the decades of the 50s and 60s, or the 40s, 50s, and 60s, right? That kind of time frame. If you have that information, you might be able to say, aha, maybe I can somehow relate that information to help me figure out how likely they won the 1952 World Series. And so mathematically, how do you relate the two? Right? That's what we're doing when we're building the model. And there's usually a lot of assumptions built in there. It's a very made up, it's just a made up process. What information do you try to link in? It depends on what kind of information. So first of all, when you build this model, it's the question of which information out there in the world am I going to try to incorporate in this, right? That's a choice. That's a design decision, right? Secondly, how do you link it in? That's very much subjective, and you're kind of having to think through it and come up with ideas on how to do it. And so this is something that we haven't really talked too much about yet, but it's actually going to be the bulk of the remaining course. Probably around, like, I don't know, a good 70% of our remaining lectures are about how you build these models. All right. Then once you've built the model, what you're going to have to do is, and you built the model, and then technically you have to pull in the data also, right? And then we have to use data to estimate our parameters. All right. And this is kind of the section that we've kind of already been working on a lot, where we were talking about, this is the whole Bayes rule, right? Where we said, well, what's the probability of our parameters given our data? And we said, aha, we know how to do this. This is how confident we are in different parameter values, or how compatible are the parameter values with the data that we have that we're bringing in. And we have the Bayes rule that we write out, right? I'm not going to write it out right here. And you just plug that in and you're good to go. Except that it turns out it's never quite that simple. But the good news is that today, in this day and age, for the most part, although we've spent all this time doing our grid approximation and things like that, this is all more or less automated by the computer. Automated by computer. So starting today, we're going to start using the computer to automatically do this for us. All right. So to do that, we're going to have to learn how to use some extra software and commands in Python, specifically PyMC3. But what it's going to do for us is, once we've built our model up, it's just going to automatically estimate the parameters for us. Once we pass them, we say, here's our data, here's our model that relates the data to the parameters that we're interested in. Do your magic, and it's going to spit out some estimates for the parameters. That's going to be pretty cool. And we'll see that in action today. Then, after we've done this, then we have to go back and evaluate our model. Evaluate and iterate on our model. I'll say and iterate. The model. And this is not easy. This is the part where, once you've done this, now that you've estimated the parameters, now what you want to do is you want to look at it and say, okay, well, what does this actually say about the real world, right? Because obviously, the thing that we don't know is something about the world, right, or about reality. And so, these models involved a lot of assumptions, right? Maybe the data was also kind of, sketchy. Who knows? But there was a lot of things that we had to come up with and make up and describe. And now when we go back and we get our estimates, we want to actually take a look at what we got out of here and what it tells us about the real world. Because when we look at it, we might come back and say, it's doing a very bad job describing the real world. Somehow there's some element of the real world that I failed to capture in here. Because of that, the results of this just look like garbage, right? This is a garbage in, garbage out. Even though this says right here with this estimation technique, it's going to do as best as it possibly can, given what you've handed it. But if you've handed it garbage, it's going to hand you garbage back out. There's no two ways about it. And we'll show a few examples of that today also. So then you got to evaluate everything. And then finally, the last step, and of course, there's probably more steps I'm leaving out, but this is just kind of general ideas here, is you need to be able to communicate. Communicate the implications and results, the results and implications. So you need to communicate, you have to interpret and communicate, I suppose. Interpret. Although I would say that interpret is kind of part of the evaluation up there. So, somewhere in between the two, you got to do it in both of them. All right. And so here, it's how do you display the information? How do you actually package it up to communicate to people? And we've talked about this a little bit in the last lecture and in the sampling chapter, in chapter 3, where we talked about compatibility intervals, and we talked about things like how Pfizer, how they chose to communicate was saying it's at least 90% effective, rather than because, and I think part of the reason why they did that, by the way, it's a little bit of a side note. If they had this distribution for how effective they thought their vaccine was, 95% and then 90%, I think that they might have been worried that this was like an intermediary result. So if they intermediate result, so if they said 95% and they collected more data and it ended up being towards the lower end here, which is perfectly possible, I have that feeling they were very averse to having to revise their estimate downwards. If they say, oh, it's 95% effective, and then like a week later they go, actually it's 91% effective. Suddenly people are like, okay, you know. But if you say 90 and then later revise upwards, then it's just a pure win, you know? So I think that was I think part of it was just PR reasons. But anyway, so how do you actually communicate these results and implications from your model? All right. So this is what we want to focus on during this class. And so one of the big things that we're going to be doing today is we're going to start focusing on building models. How we actually use the length, how do we write it out mathematically, and how do we put them into the computer? And then secondly, when you're confronted with a bunch of data, how do you try to link that up based on the form of the data? How do you link that up into your parameters? All right. So, like I said, so up till now we've kind of been focusing on 3 and only a little bit on 5, but ultimately 3 we're kind of more or less done with that. We'll come back to it a little bit in chapter 8, I believe it is, when we talk a little bit about how the computer is actually working its magic. All right. But that's more of just for our just so that way we know. And then every now and then the computer can mess up. And so when it does, we can look at it and actually identify when it's messing up and try to figure out ways to fix it so that way it can actually better correctly estimate the parameters. All right. But all that stuff with the grid approximation, we're pretty much throwing that aside now. All right. We've looked at it, we've tried it out, it was pretty cool. We kind of understand the idea. But ultimately, we can't do that for larger problems anyway, because once we start moving into worlds where we have dozens or hundreds of parameters, part of the problem was that we had these little grid sizes, which were like 100 long. And then now if we have 2 parameters, what's interesting is that now we need to figure out not the parameter of, let's say, just theta, but now say theta 1 and theta 2, because we have 2 parameters given our data. Well, now what do we have to do? We have 2 parameters here, and they could be dependent on one another, where maybe when one is high, the other one is high. That's when they're correlated. And then so what you have to do is you have to make a full grid. And he actually does this in this chapter, in chapter 4. He does this where he makes a full grid for the two parameters in one of the models, right? And you ask, okay, well, how big does this grid have to be? Well, we have to have 100 possible values for theta 1, and then we have to hunt 100 values for theta 2, and ultimately we need every combination. So that ends up becoming 100 squared, which is, and this is by 100. I think in the grid size, we're oftentimes doing 1,000. With 100, suddenly for doing it for two parameters, it is 10,000 numbers that we got to evaluate at, where we have to take the likelihood times the prior. But if it was 1,000, we'd be at 1,000,000 already, which is an awful lot bigger. And then I tell you, well, sometimes we deal with 100 parameters in our model. And by the end of this course, we will be doing 100 parameter models. Like, they really aren't that big a deal, right? Uh, and so now suddenly we would have to have 100 different dimensions here. This is called the cursive dimensionality, because now we would need 100 to the 100 power, which is 10 to the 10 squared to the 100, which is equal to 10 to the 200. And of course, like the max that we can maybe handle is probably something like 10 to the 10th ish. 10 to the 11th is the most that we can really deal with on a computer. Yeah, 10 to the 9, 10 to the 10 is usually about what we would consider reasonably okay. And so the problem is that this thing has, it can we can handle 10 with 10 zeros. This one has 200 zeros. So we definitely can't reasonably fill this in. This is only with 100. If we want to do 1,000, it would be even worse. So it would be 300 zeros. So real bad. And so in general, that grid method doesn't really work. Doing it mathematically, if you're interested in doing it mathematically, I actually have a few examples on actually solving some of these problems mathematically. I'm not going to do it in this class, but in another class that's a little bit more math focused, I'm going through some of it. I'll post the link for it in the description. Only watch it if you're interested. We do a couple derivations with normal distributions and the t distribution ultimately, which is pretty cool. And then also one where we derive the basic least squares regression, and it's all just using the basic Bayes formula and just plugging in. But I'm not going to do it in this class because I think I just want to focus on less on this stuff and more on the building of the model. All right. So, we can do some stuff analytically, but also that breaks down very quickly. Uh, Anything but the simplest of problems you can't actually solve analytically to get useful results. The math just ends up being impossible because you have to do lots of integrals, and lots of integrals you just simply can't do. And a lot of times you'll have to do like 100 integrals, and it's like, well, good luck. Nested integrals, right? So good luck. So we end up having to use the computer for it. Either way. And then, so in chapter 8, we'll actually talk about how they do it. But for now, we can use it without knowing the details on how it does it. All that you need to know is that when it estimates the parameters, the way it does it, it can't actually hand you like a function or anything, or like a graph of it. All it can hand you is samples from your posterior distribution. So just like how in chapter 3 we started to sample from it, that's all we're going to get from our methods that the computer uses. That's the best we can do. That's the best the algorithms can do. So now then, I just ranted for 20 minutes on that. Sorry, guys, I'm not cutting it out. So anyway, now that we've done this, let's actually start building a model. So we'll go back to the question that kind of started everything, as silly as it was, which is people's average height. So in this case, we're going to be using data from, I'm not going to get this right, how to pronounce it. I'm just going to ignore I believe it's the Kung data set, right? Looks like that. And that is the name of of a tribe in Africa, as far as I know. And what happened was an anthropologist had gone in and actually like measured everybody's height, got their ages, and did a bunch of stuff with it with this tribe. And this exclamation mark is actually like a click sound. And so, like I said, I'm just not even going to try to do it. I think McAuliffe actually does it in his lecture. He actually says it pretty well. I think he says it once. But anyway, We actually have data on them on all their weights and heights and their ages and whether or not they're male or female. And what we're going to do is try to estimate their average height, right? We're just going to estimate the average height. That's what we want to know. So, what don't we know? Their average height, which I'm going to call theta, right? Theta is their average height. All right, cool. And what do we have as data, right? What's the information do we have? So we're interested in this kind of amorphous idea, which is the typical height of this type of a person in this tribe. And what data do we have? Well, we actually have, I think, pretty much all of their heights. So technically, we don't even have to do statistics since we have the whole population of the tribe. We just simply take the average of all the measurements and you're done. But we'll say that I don't actually know the details. It might be that they only got a subset of the tribe. So if you assume they only have some small some sample from the tribe, we need to figure out what it is from the sample. All right. Now, how do the two relate, right? So what we have, so this is what we want to know, right? This is a parameter we want to know. And what we actually have as far as information is the heights of, I believe, something like 352 adults, I believe. Once again, we're going to drop out the children because I think what I talked about in the last lecture was that one problem is, of course, with the kids, you know, they're shorter and they're lighter and they aren't like fully grown yet. And it's like you got adults, with time, you know, you kind of peter out at what your height is. And so, you know, we're just going to be looking at these folks here that have already reached full height and not looking at the kids, right? They mess things up. We can model them later, but we won't. I think he does it in chapter in the one of the last section of chapter 4 that I have you read. I'm not going to do it today, but he fits a nonlinear model to get the heights of the kids. Yeah. All right. So anyway, so we have the heights of 352 adults. So now the question is, oh, and we also have other information, or the info we have, right? So we have this. We also have a bit of other information, which is we have some information as far as what we think would be reasonable average heights, right? We know of some reasonable average heights just from experience, right? Like if I were to tell you, oh yeah, their average height is 8 feet, you'd be like, I don't know about that one. I doubt that. Or if I told you their average height was 2 feet, you'd also quite doubt that, right? So we have some actual idea on what typical average heights are. And so we can use that to help also figure this out. And this will go into our prior. This is going to be going into our likelihood ultimately. All right. So now, how do we relate this information we have towards this parameter, which is what we want to know? All right. So the way we write it is that we're going to have to pretty much assume some distributions on things. That's what our big assumption is going to be, and this is how we're going to model it. So what we're going to say is that before we even look at any data, I'm going to assume that data is going to be distributed somewhere. This is what I think, just based on all this other information I have as far as reasonable heights are concerned. I'll say it's normally distributed. Why normal? Because we talked about this before, the central limit theorem, and it's more of an epistemological argument, which is that um, I think personally, like, okay, I think it has some roundabout average value that I would guess at, but there's some range of what it could be. Now, in the book, I'm going to stick with, I think, what he uses in the book, which is 178 and 20. And I'm just going to use it what it has in the book, just that way the results I end up doing matches with the book, even though I'm not particularly wedded to it or anything. What is the 178? Well, first of all, this is in centimeters, right? So now we're going to have to do the conversion here if you're like me. And what is 178 centimeters in feet? Let me plug this into Google real fast. 178 centimeters in feet in height. Oh, let me see here. I was typing in feet and inches. There we go. If we can get it in inches. Oh, well, it's 5 feet and then 5.84 feet. Let's see here. That translates to, aha. Here we go. 70 inches. So it's 5'10". All right. And the reason why he chose this is that it's his height. So he goes, oh yeah, well if I don't know any real guess, I'd say, oh yeah, their average height is probably my height. Now I think, and I'm about the same height. I think it might be 5'9". I don't know, 5'9", 5'10", somewhere in there. And then right here, this is our standard deviation. So this is saying before we even see any data, if we had to guess how tall they were, it would be somewhere like around 178, and they could be on average taller, could be shorter. Now, 20 centimeters, how big is 20 centimeters in inches? Let's see that one. 20 centimeters in inches is about 8 inches. So it's plus or minus 8 inches thereabout, right? So we wouldn't be, so our guess is, here we go. Our best guess is 5'10", just because why not? But it's possible that they're actually down here at, say, 5'2", or it could be that they're all the way up here at like 6'6", which is obviously pretty high. Personally, I would have probably shifted this over to the left, because I know usually these tribes are usually shorter in general, just because they don't have the same level of like nutrition that we have in our worlds today. And, in these, like, first world economies and such. But still, who knows? So there's a pretty wide range. And what we'll see is that even stuff that's even wider further out there is still perfectly possible to, it's not like ruling them out, because this is a pretty wide interval, right? Like I think the 89% interval would probably be something like 4'8" all the way up to 6'10" or something, right? Some huge range of possible values. And the idea in this is that before we see the data, I mean, we don't have that strong of beliefs, and so this is coding something that isn't particularly strong, isn't super binding. It's not like, oh geez, totally unreasonable estimate. Like, oh yeah, we're pretty sure it's between 5'9" and 5'10". It has a wide range, and it's pretty reasonable. And so this is taking in kind of just our basic idea of saying, look, we know it's not 8 feet, we know it's not 2 feet, right? And then the other thing is we have these heights from all these adults. And so now we got to say, okay, well, what are these heights, right? How do we model the heights that we actually observed? And the way we do that is we say that the height for a person, and I'll actually use HI here. Typically, you use YI just for the data. Y is the data, but we can also use HI here, and that's going to be normally distributed about what? So the idea is this: is that their heights, we believe, are going to be centered on some average value theta, right? That's the average height of somebody in the population. But they obviously aren't all going to be exactly the average. There's going to be some variance there, right? Maybe some of them are much taller, some of them are quite shorter, a lot of them are nearby the average, right? But there's going to be some variance there. And so what we're going to do is we're going to describe, once again, how do these heights relate to the average? Well, the height should, on average, be centered on the average theta, but there's going to be some variance with them sigma, right? Sigma squared, all right. They have some variance about it, and we're going to assume normality because, well, we just tend to assume normality, right? We can do other more complicated stuff if we really wanted, all right? Like we could have said, okay, average heights for men and women are separate, right? There's extra stuff that we could be putting in here, right? But for right now, we'll just keep it nice and simple model, all right? There's a lot more we could do with this, all right? But now we've successfully related how it is that these two pieces of data relate to the parameter of interest. Here we have that the heights that we observe should be centered on the parameter that we're interested in with some variation. And then secondly, we can say ahead of time that we believe that the parameter we're interested in should be somewhere in this neighborhood. All right. So now we've successfully done this step of building the model, of incorporating all of our outside data to help us figure out what we're actually interested in. And now we're ready to just plug it into the computer for it to spit out. Well, once we actually put in the data too, it'll just spit out what our best guess is to the actual average height of the tribe. All right, that's pretty cool. All right, but this is how we approach problems in statistics. All right, and so I've written this very explicitly. This way of writing it is what we're going to be using to write models pretty much for the rest of the semester, where you have this little uh, tilde here showing distributed as. All right, that's how you read it. So the parameter theta is distributed normally about 178 with a standard deviation of 20. Oh, and one other thing here that's kind of interesting. What's sigma here? That's a fair question. What on earth is sigma? Sigma is how much variation there is in the population. We don't know that. That's something we don't know. Now, in this case, it's not something we're actually interested in, right? What we were interested in was theta, parameter here, was our theta, which was the average height. That's what we actually wanted to know. But it turns out that there's also something else we don't know, which is what the variation is in the data around this average height. And so, unfortunately, because we don't know it, that's something else we're going to have to estimate. So we actually now suddenly are stuck with a second parameter, which is the average variation of heights from the mean, from theta, right? Average height. So unfortunately, in order to actually incorporate this data that we have observed from these 352 observations here, in order to actually incorporate it, we have to estimate a second parameter, right? And unfortunately, do we have any information on how much typical variation there is in human height from the average? Well, yeah, we do. We do at least have some reasonable estimate to what typical variation is. So we should incorporate that extra information as well. So we're stuck with having to do a little bit more work to build this model out because we've added, unfortunately, this second parameter that we actually aren't even interested in. In fact, this parameter, this type of parameter that gets added just because we kind of need it to mathematically do things, this is called a nuisance parameter. Oftentimes you estimate it and then you just never look at it again, right? You're like, okay, yeah, I have to estimate it just to actually use the data and incorporate it all. But other than that, I'm just going to pretty much throw away the results. But every now and then, it could be something that you're interested in. You could be interested in what the variation is among people. So what I believe McElrath does is he says, we don't really know, you know, we know what typical variation is to some degree. Maybe the average height, you're going to be the average height plus or minus what? Maybe like a couple feet, 1 or 2 feet, maybe, right, at most. And so what I believe he does, that he says that he guesses that the variation for sigma is going to be uniform from 0 to 50. Now, this is actually kind of unusual distribution that he uses. But what it says is that people could be everyone's dead or on the upper end of things, it could be that the average person is, that the typical variation is plus or minus like, I think 50 centimeters translates to about 2 feet. Let me look at that up real fast, just that way I can say it reasonably confidently. Uh, 20 inches. So that's about 1.5 feet. So it could be 1.5 feet in either direction, right? And then, of course, that's just one standard deviation. So, like, 2 is plus or minus 3 feet, which is pretty huge, right? If this was actually 50, if there was actually 50 for the variation, that would mean that like 90% of people are within 3 feet of the average. So if the average was around 6 feet, it would be everyone's between 3 feet and 9 feet, 90% of it. I mean, that's totally overkill. We know it's probably going to be less than that. But we'll see. We'll give it anything just because who knows. Typically, like I said, typically when you do Bayesian inference, you don't. This is a kind of an unusual prior here, but it's okay. It's not going to hurt anything as long as we give some reasonable estimate that we aren't ruling out reasonable values by accident. It's going to be okay. And of course, one thing is it can never be negative because we're talking about the variation here in the population. Of course, the variance can never be negative. So now that we have this, let's look at how we actually implement this on the computer. So I'm going to have to grab the data and actually implement this model on the computer. All right. All right. So let's see here. What have we got? You can see me Googling all this stuff. So, okay. Here is our new file, which I will call really fast. Let me name this for us. Phase week 4, week 3, right? Week 3 lecture. Cool. All right. So to start with, we have to collect the data. Now, I've posted it in the Discord now, which is the this is the GitHub for the textbook, and actually it's also for all of his R package and stuff. But in here you'll see data. So if we click on here, we can see this is all the data sets that's used in the book. And I believe in this book, in the book for the data set that we're looking at, he will always say data and then in parentheses say the name of the file. So in this one is data and it says Howl 1. And this is in R code 4.7. You'll see it says data Howl 1. That's when he loads it in. So what that means is that the data we're going to want is right here, is Howl 1. And then what you do is you can click on here's the data set. They have height, weight, age, and then whether or not they're male. 1 for males, 0 for females. And if you just click on raw right here, it'll actually take us to this little website right here where it just has all the data, just the raw data right there as a CSV. And what we're going to do is we're going to pull this in to our Google Colab. Usually, if you want to, you could just download all the data, and then in your if you're doing this on your home computer and not on Google Colab, but on like your own little Python editor, then you can import it easily enough from there. Here, we're going to actually download it directly from the web URL, and so that'll be handy. So now today, what we're going to do is we're going to start using all the remaining packages that we have to introduce this year. So we've already introduced, let's see here. I talked a little bit about SciPy. So we have to import SciPy.stats as stats typically. And so this has all the common distributions. So lots of times what we'll see is that another package also has them. And we'll typically use that one for doing our Bayesian inference. But sometimes we just want to draw some random values, look at the PDF or PMF of a distribution or things like that. So oftentimes you'll have SciPy. And sometimes they have other useful special functions and such that are valuable, like the binomial coefficients or things like that. All right. So we have that one. We have, let's see here, we have matplotlib. We've introduced already. .pyplot as PLT. So that one is for plotting, typical plotting. We've done NumPy, and that one is for doing vectors and handling vectors. So that's a typical one we do. We also finally did RViz. Let me pull that one up right here. And this one's actually probably one of the most useful ones. This is specifically for handling, and this one we had to import in this special way. And you'll just be able to copy this from the link on the description here because it should take you to this file. This right here, because unfortunately it doesn't come default. Google Colab only has so many of these packages already pre-installed. They don't have RViz because it's just not that common, sadly. It will be with time. It'll become more common. And so that one, you have to first download it. And so here's the link that will download it. So it sits here and it installs it first. And then once it installs it, then it's going to actually import it. Oops, I did not mean to already run that. Oh, well. And then finally, now we have one last one we got to do here, which is PyMC3. And PyMC3 has all the functions for handling the estimation of parameters from our model. So this is in PyMC3 is where we're going to write up our model, and then we're going to be able to get all of our estimation from it. Now, in past years, I'm going to be quite honest with you because while I teach this stuff right now, you'll see that there's going to be times in which I kind of forget how to do things. And the reason for that is that, sorry, I didn't mean to pull up that file. The reason why is because in the past I've been using a different library for doing the estimation. There's like 8 different ones you can use in Python. And so I just started to switch to PyMC3 just the last few weeks. So I'm still trying to learn the ropes with it. So we'll have to both kind of learn it together a little bit as we go. So I'll frequently have to look some things up, which is okay. Luckily, we have already for us um, this whole GitHub right here, which is also on the Discord, where they translated everything in the book, all the code in the book, into PyMC3. And so luckily we can use that to help guide us a little bit. All right. So now then, back to business. So we have all these imports. That's great. So that loads up all of the different packages. We still have to learn. Oh, wait, nope. There's still one more package. I forgot. I'm sorry. Sorry to break it to you. So let's hear. So we've already been slightly introduced to these 4, but we're obviously going to have to learn them more if you don't know them already. At least these 3 are all very common. This one is these 2 down here are specific for our Bayesian stuff, statistics stuff. But there's one more that we need, which is going to be pandas, right? And pandas is a very common one. And what it does is it handles data sets. So something like this, tables of data, pandas handles it and helps you manipulate it and load it up and things like that. So one nice thing about it is that pandas here has a .read CSV command. And what it does is typically you give it a file name and it will load up the data set and store it in a nice little format that's easy to manipulate. You can also hand it a URL and it will download straight from the URL and plop it in there. So here's the GitHub file that I had, and now I hit Shift Enter, and as you can see, it reads it. Unfortunately, it has a problem doing it. You can see it is not formatted nicely, and the reason why is that by default, CSV stands for comma separated value format, and this thing actually uses McDonald's for some reason uses semicolons a lot. It could be that sometimes you have like names of things, like if you can imagine like if you have like Seattle, Washington as like a cell, as one name is like the name of a location. It will do Seattle, comma Washington, and so sometimes people use a comma when they don't actually mean to be separating it into multiple columns, and that can mess things up. So some people like to just use semicolons because that's something you don't typically see in data. So to do that, though, we have to say separator equals semicolon. And now pandas will know, okay, it's semicolon separated, not the comma like I would normally assume. And now you see it's very nicely formatted, where you have the heights, the weights, the ages, and then whether or not they're male. All right. So we've loaded this up. And before I forget, there's also some other standard type of what I would call boilerplate code that we want. And that is, let me scroll up to the top here. I think I have it in here. That's not quite what I want. Let's see here. Here it is. So there's some boilerplate code that, so like frequently what we're going to see is that every time that we start up a file, we pretty much immediately have all of our imports. This one even has one more Seaborn right here, which we're not going to use in this class unless you want to. It's another plotting one, kind of like PyPlot, but a lot of people like it a little bit more than PyPlot. So sometimes people will make more complicated graphs using Seaborn. Or simpler plots using Seaborn that just look by default nicer. So you're welcome to try to learn that one if you want. We're not going to use it. So, but every single Google Colab that you open up, pretty much like the default should be, okay, copy and paste this stuff in from some, maybe you just have like a little notepad file .txt that has all this stuff and you just immediately copy and paste into your Google Colab every single time that you open up a new one. And then down here, we have a little bit more, which don't want the watermark one. And all this stuff does is it configures some of like the default for like, here's the random seeds. So that way, anytime we do random numbers, we'll get the same result if we were to clear everything and run it over again. This one right here is the default, the type of figure formatting, so it's how you actually configure some of the figures that we make, so that way it looks nicer. Same thing with this one. This is any RViz plots, some of the default styling of it. And right here, which is really interesting, is RViz right here. You see that we've already used this HDI before, the highest density interval. What this does is this sets it so that way the default range is 89%. And why does he do that? Well, because that's what McElrath uses 89% everywhere. That's kind of his default rather than 95% like you see typically. He uses 89% just to emphasize the fact that 95% is a totally arbitrary number that statisticians have just kind of used for traditional reasons. And so he's using 89% for some, I think he says because it's prime. So he's not looking for a very good argument for why. That's just what he's going to do. All right. So that's cool. And so this will do it so that way now, whenever we call HDI, we don't have to specify, oh, yeah, we want the 89%. It'll just automatically do it for us. So that'll be cool. You see, they call it a credible interval. What we're interested in, in the book, he calls it a compatibility interval. So, but it's hard to have it to break. I'm going to call it credible interval lots of times rather than compatibility interval, just by just because that's the way I learned it. So anyway, now back to the matter at hand. So now we have all this boilerplate, which is great because you can just save this and then every single time you open up a new Google Colab, just paste these in and you'll be good to go. So now we have this data, and this is called a data frame. A data frame is what it's called. No, it doesn't label it there, but that's what it is. So in Pandas, they call these data frames for the tables. And so a frequent thing that you'll see is people will call it DF is equal to, and that stands for data frame. So a data frame is equal to this, right? Now we've stored the data frame, and we can print it out. We can say dot head, for example. Oops, I need to put parentheses around it. And the head gives you the top 5 data points, and I think it probably would have tail also for the end. So those are the last 5 data. And you see we have 580, 544, I believe. Depends, does it start off at 0 or 1? Let's see. Starts off at 0, so 544, but a lot of them are kids. Once we get rid of them, I think we'll have 352. All right, we can also do things like, say, give us all the weights, right? So you say df.weight, and it'll give us this column here of the weights. And there they are. Now you'll notice that it's still inside of some weird different format here. If you want to, you can also say dot values, and it will convert it into a NumPy array for us. So if you ever want to just get it out of this data frame format and instead use it as just a NumPy array, you can do the dot values there. All right, and we'll do that every now and then because sometimes we just want the raw numbers and mess with the numbers as like a normal array. All right. What we want to do here, though, is the first thing we want to do is get rid of all the kids, right? So we can call this like df2 or something. And what we need to do is we need to select out, and we need to select only the adults. And so what we do is we can say df.loc. And what this is going to do is going to access a group of rows or columns. All right. And so there we go. And the way we do this is that we have to specify which rows or columns do we want. All right. So in this case, the rows that we want are only the rows for the people who are not children. So what we do is we say, we look at df.age is greater than 18. And let me show you this really fast, what this is actually doing. So if you say df.age, right, this grabs us the column of ages, and we say greater than 18, and now what it does is spits out, okay, yeah, this person's an adult, these are all adults, this person is a child, this person is a child, right, and these are adults. And so what happens here is that, let me just make sure here, greater than or equal to 18, I should say, just because, once you're 18, you're an adult, right? So now that we have greater than or equal to 18, these are the ones that we want to keep. All the trues are the ones we want to keep. Falses we want to get rid of. So what you do is you just say, select all the rows, this is the select part, select all the rows where this is true. And so now when you run this, now our df2, what you'll see, if we run this, it'll still show these indices, But you see it skips some now, and that's because it skips all the ones that it got rid of. And it says there are now 352 rows, not the 544 like we had with DF with the original data frame. 544 with 4 columns. Now it's down to 352 because we've gotten rid of all those kits. All right. So now that we have this of just the kids, now what we want to do is actually try to figure out their average height. Right? Here's all their heights in centimeters. Which, by the way, what was our center? Our center was 178. Oh, these folks are a lot shorter than 178, aren't they? So they're going to be on the short end of what we thought, which is fine. All right, let's figure it out now. So what we do is these guys are all what, like 5 feet? Okay, that's kind of short. That's modern nutrition for you. So now then, let's actually try writing up this model. So there's going to be a little bit of it which won't entirely make sense, which is fine. But some of this is just kind of this is how you have to do it, right? And so once you've done it a few times, you just got to practice 5 or 6 times, and then it'll be natural for you. All right. So we'll call this. So right here, what I'm going to do is I'm going to give it a name, the model a name. So here's like M height. Right, there we go. This is a model for the height. And this pm.model says that this is going to be a PyMC3 model. All right, so this is a PyMC model, PyMC3 model, and its name is M height. Now what we have to do is write up the model in this. All right. So we say theta is equal to, now I'm going to write it in here, and then we're going to look at it, and we're going to compare it to what's on the board, and you're going to see it's the same thing, just easily translated over. All right. pm.normal theta. So just bear with me here while I write this, and then we will talk about exactly what it all means. All right. It'll hopefully look pretty straightforward. Sigma pm dot, and maybe I should be a little bit careful with using sigma twice here, but this sigma and mu and sigma are actually more like, are not actually the same. This sigma is not this sigma. Let me just say that. All right. You can also, if you want to, have just written this. I was just being explicit that for this normal distribution, it's centered on 178 and it has a standard deviation of 20. All right. And then so right here, sigma is uniform distributed according to our uh, prior. And then we have lower equals 0, upper equals 50, we said. All right, I'm going to put these mu and sigma back in, just to be clear, that this is not, that these are not the same. All right. And then finally, we have our heights. And our heights are supposed to be normally distributed, we say, centered on theta, right? So first we have to give it a name. We have to do that. Mu is equal to our theta. And our sigma is actually equal to sigma, right here. Sigma is sigma. And then finally here, we have to pass in that we have actually observed this data. And the way we do that is we say observed equals df.height. So now let's quickly take a step back and compare this to our this model we just wrote to what we have on the board. All right. So you'll see I said theta is normal 178.20. Right? And we'll see that right here. Theta is normally distributed about 178 and 20. The sigma is uniform 0 to 50. And then each one of the heights, right? The I here indicates a single given height is going to be normally distributed about our theta with standard deviation of sigma. And so here we go back to the code and we see that's all that we're doing, right? We just say, okay, theta is a normally distributed variable, right? And then we always have to give it a name here. This is just more of a Python thing. This is making sure that the computer knows everything, because later on you could technically name these, have these names mismatch, but you almost never do. I wish they were default to just naming them, but you got to specify it, unfortunately. This is just a kind of a quirk of the language. I wish you didn't have to. It would make things a lot simpler if you didn't. Anyway, and then you just say, okay, it's a normal distribution centered on 178, 20 standard deviation. The sigma is uniformly distributed according to our prior, with centered on 0, standard deviation of 50. And then finally, the heights are centered on theta, and the standard deviation is sigma. Now, one thing that you need to notice here is that I did not, while on the board, I have it going first. I have the heights going first, and I'll almost always write it that way. In the code, I always end up writing it the other way. And that's because if you have it first, you actually get an error, because right here, you're using theta and sigma, right here, theta and sigma, but they haven't been defined yet. So you actually have to first write what they are, and then you write this one. So while on the board, I typically start with the how the data is distributed, and then the priors go at the bottom. In the code in Python, I will almost always write the priors first, because they don't rely on anything else, and then I write the stuff that rely on the priors underneath. That's just the only thing that's really changed is the order that we're writing it. All right. And then the last thing that we have to do, this is our model, that's great. But the last thing we're going to have to do is we're going to have to get what is called a trace. All right. And this is really just the samples. In fact, we can even, if we want to, just call it, we can call it samples, but the traditional name is called the trace, right? And what you do is you just say dot sample, all right? And then you say how many samples do you want, and that's it. That you also, there's a lot of optional parameters, but what you're going to do is say, okay, given this model, give me 1,000 samples of the parameters. All right. So once again, it's going to do all the Bayesian calculation stuff, doing the likelihood and the prior based on these distributions you gave it and the model you defined, and it's going to give us 1,000 random samples of our posterior. All right. So when we run this, it's going to take it a minute to start up, and we'll see it run as it tries to go, okay, I'm going to do these calculations for doing the sampling. And it actually takes it a little bit to do, and that's just doing a lot of optimization behind the scenes. And I think it's compiling some stuff into C++. Who knows what all it's doing. So we give it a minute, though, and here it goes. And we'll explain about what it's actually, how it's algorithmically doing this, and like I said, in Chapter 8. But right now it's initializing the no U-turn sampler. That's actually kind of weird that it uses NUT sampler when really, I believe NUT stands for no U-turn sampler. So, it's technically the no U-turn sampler, kind of like ATM machine. But anyway, it's going through, it's initializing it. This is actually taking a little while. One reason why I used to not like PyMC3 is that it was very slow, but they are going through and changing the backend to speed it up. So it was doing all that initialization. Once it actually started to sample, it was like instantaneous sampling. And that's because it's a really small model. So lots of times for small models, it spends more time actually prepping everything than it does actually doing the sample. In larger models, it spends all this time spinning up and getting everything ready because it actually optimized everything behind the scenes. So that way, the sampling is usually the thing that takes the longest. And then if it does all this extra preparation, then that goes by a lot faster. In this case, it's kind of the opposite. It probably could have gone away without doing as much optimization and just started sampling. Now, what you'll see right here, it says nuts, and then it shows sigma comma theta. What's that? Well, those are the two parameters that it needs to sample, because our posterior, it knows, okay, we've already observed the heights. So clearly that's part of the likelihood, and that's not something that we're trying to estimate. We don't want to estimate the heights. We already have that data, but we don't have anything for sigma or theta. So for those, we're going to need to try to estimate them. So it already knows to do that. And now let's see here. Now what we can do is trace height. Maybe I shouldn't have named it something that long, but then we can say, let's see, we can say of sigma, right? And now this is, like I said, these are all just our samples. So when we say of sigma, when we run it, this is what it spits out. It spits out all of our estimates all the different samples for sigma. And what we're actually interested in, that's something that we're not interested in. So let's grab out the theta here. This is the average height. And you see it's hovering around, what is that, like 140? Really low, actually, huh? Wow, 140. Whew. Let's take the average of that, right? So how do we take the average of that? Or we just say np.mean of it, and that gives us our average height. 138 centimeters. What is that? 138 cent. Whoa, what is going on there? Somehow I have caps lock on. That is very disconcerting. I actually don't know how to turn off caps lock because unfortunately I disabled my caps lock button forever ago. So I don't know how it did that one. Okay, there we go. 138 centimeters. There's no way caps lock could have. It must have been the shift key was stuck. Centimeters in inches. 54 inches. Wow. That's incredibly short, isn't it? Is that true? Man, are they that short? I'm impressed by this one. Let me see this real fast. Before I go on, let me see here. Yeah, it shouldn't be that short. What have I done? That makes me a little bit concerned. But I believe they should be closer to like 155 centimeters. So I'll have to take a look at this. What did I do? Did I do less than? Did I grab the wrong set here? Oh, do you know what it is? I said df dot height. That's my problem. df2 is the height of the adults, right? df was everybody. df2 is the height of the adults. That's why. So I was including the kids in there by accident. Let's quickly rerun it. Luckily, all that setup time, it actually stored it and kept it on hand. This warning is not an issue here. We'll ignore it for now. Later on, we'll talk about it. It just says, but right here, it says, try to increase your number of tuning steps. So we can always do that. We can actually just say right here, tune equals 1000. By default, you can see right here, it does 500. And what it's doing is trying to figure out some of the parameters that it should use when it's actually doing the sampling. There's some meta parameters or hyperparameters that it has to choose. And when you do it with 1000, you give it more time to try to figure things out. So that way it can usually, when it comes time to actually sample, it does it a little bit more reliably and gets better results. So anyway, here we go. Now we get 154. Thank goodness. All right. Now, real fast, I forgot to do this, and this is something that's very important that I want to talk about. And he talks about it in the book, and I think it's really worthwhile to talk about here. We have our priors ahead of time, right? Or we're supposed to choose these priors, and I kind of just made some up, right? But just because we make it up doesn't mean that we can't, we don't just pick something and go with it, right? Here I kind of did because I already knew that he had gone through all the thought process of it. But what would happen? But one thing that we should do is actually try to evaluate them before we go off and use them. Because, in this case, it's like, okay, the theta and the sigma are those values. Like, what does that translate to in the real world, right? The one thing that we actually observe, we don't actually observe the average height or the variation. We don't observe it directly. What we do observe is typical heights that we see, right? We see people's heights. And so what we can do, and by the way, 1 second here, before I go on, I just want to make sure, how short are these guys? 154, weren't that centimeters? Let's see here. Centimeters and inches here. Let me make sure here. All right, 60 inches, that's 5'1" average. That's a little bit better than I was like, man, they're like only like 4'2" or something. What's crazy with these guys? They're like kids. you know. So anyway, 5'1" is still quite shorter than the average person here, but much more reasonable value. So anyway, so before although we've already gone ahead, typically what you want to do before you start fitting this is evaluate your priors. And so we'll do this in a minute also again when we come to the linear regression, which we'll be doing in just 1 minute. All right. So with this, let's first look at our priors. So the way we're going to do this is we'll just say stats dot normal dot RVs, and that's how you sample from a normal distribution, get some random values from it. All right. So we'll do our prior thetas are normally distributed about I think you can just say loc equals 178, scale equals 20. You might also be able to say mu and sigma, I'm not sure. But here's a bunch of here's just one prior theta. We need to actually do a lot of sample of it, right? Oops. Right, that just gives us one. And what we want to say is, hopefully, I believe you can, for RVs, I think you say size right here, which is how many of them you want. So let's grab, let's say 10,000 of them, or 1,000, whatever. Let's do 10,000. So we have 10,000 of these betas, which are from our prior. And then we have our sigma, our prior sigmas, which is stats dot uniform dot RVs. And then those are, I don't quite know how to actually define this one. I'll have to look up how you actually do this one, because you have to look up in the doc string for it. So let me do that. SciPy uniform distribution. A lot of times I don't know how these things work, so we got to look about it. So for this one, it says the uniform goes on. So if you specify loc and scale, then you get a uniform that has lower end is loc, and then upper end is loc plus scale. That's important to know. So what that says is that in this case, our loc is 0, and our scale is 50. Right? So therefore, the end is going to be 0 plus 50 on the upper end, and the lower end is going to be 0. And once again, we'll grab 10,000. And then finally, we can say our prior heights. What we'll do is we will sample some heights. All right. And so each one of these should be stats.norm.rvs, and the loc is going to be the prior thetas, and the scale is going to be equal to the prior sigmas. And so what I'm going to do, so the way I wrote this, you could do it a lot of different ways. But in this case, what I've done is I said, okay, get some thetas, get some sigmas, and for each one of them, right? Let me print out prior sigmas here. Oh, I haven't run it yet. That's why. There we go. All right. So here, for example, we say, okay, in this one sample that we decided to think of, beforehand, the mean height was 171, and there was a 32 for the sigma. So there was a lot of variance, right? So that's one way that before we looked at the data, we thought that the population could be, right? They could be centered on 171 and have a large variation where a lot of really short people, a lot of really tall people, right? Now, given that, just draw one sample person from it, right? So just do a normal distribution centered on 171 with 32 standard deviation, right? Just draw one. It might be 171. It could be one standard deviation above, which would be over 200 centimeters. Or it could be one standard deviation below when it's 140, or it could be two up, two above, two below, or anything in between. And we have that. So we get one there. That's one sample. Then we move on to the next pair. All right, this one, they were 168 centimeters on average, but they were all right around the same height there. And so now when we do that one sample, it's going to be pretty close to that value. And we do this for all 10,000 of them. And once we do this, we'll have 10,000 simulated heights. And that should give us a good idea on what kind of heights we expect to see. All right. There's several ways that we can simulate this. This is just one of them. And so now we can do a plot KDE of the prior heights. There's a few ways that we can do it. I'll show you an example on how you can do it a little bit differently in just a moment, actually. So here it is. This shows the typical heights that you see. Now, 100 centimeters is what? 3 feet something, right? Let's see here. 100 centimeters in feet is 3 feet 2 inches. 3 feet. Sorry, 3 foot 3, which is obviously way shorter than the typical person. And 250 centimeters, just for context, is over 8 feet tall. And so when we look at this, this says that, it's a little bit ridiculous actually, but that's okay. It says that, the heights that we might see some people who are above 250. We might see, some people above 8 feet, some people below 3 feet, which is already kind of ridiculous. So we could have probably reined it down a little bit, but at least it's within the ballpark of what we're talking about. All right. So his example that he gives here is that the tallest person ever was at a height of, I think he says 200 and, oh boy, let's see here. 272 centimeters tall is the tallest person ever. So right around here. And sure enough, it says, look, it should be really rare to find somebody above that. Not rare enough. It should be like 1 in a billion or less, but, what can you do? But imagine if instead of this, we had used a larger prior, one that was less certain, right? So in this case, the thetas had a wider range, right? We were less sure about the average height. If we did that and we repeated this process, now this is what it looks like. Which now we look at this and we go, okay, this is a little bit ridiculous. This says only that some people are below 0 in height, and that a huge percentage, something like 30% of people, are taller than the tallest person ever, right? So you sit there and go, okay, this is a pretty ridiculous idea, right? Like this is not a reasonable plot. This is not some reasonable priors here. All right. Now another way to visualize this, in this case, what I did was I drew one height at a time, right? But you could do this a little bit differently too. You could instead do the following, right? We have our theta and our sigma, and what we can do is for I in range of, let's just do 100 here, just for the sake of argument. What we're going to do is we're going to plot the normal distribution that this thing corresponds to. All right, and let me switch this back to the 20. Now, I don't think he does this in the book, strangely enough, even though I think it's a pretty fun exercise. What you do is you say, let's just do one of them first, because I have to remember how to actually do it. Which is, I think you do stats.norm.pdf. And then what you have to pass in is, first of all, at some value. So let me just show you how this works. And then you can do prior thetas of 0, prior sigmas of 0. And that's our loc and scale. So just to show you what this is doing, is that when we run this, what this will do is it'll spit out how likely is a height of 100 if this is actually the population's distribution, where it's a mean that's centered on 180, standard deviation of 46. So in this case, 181 should have the highest value. So right here, this is 0.002 about. At the highest is 0.008, where it's like 4 or 5 times more likely at 180. And then meanwhile, if we go too high, like 220, we see us falling back down again. But it falls down slowly because the standard deviation is large. So what we can do is we can plot this. So we can do some linspace. We'll do something like this. We'll say heights or heights or theta. What do I want to call this? We'll just call this X. All right. Come up with a clever name? No, we'll just come up with X. Let's go 0 to 250, which is kind of the range of, well, let's actually keep a reasonable range here, right? The typical height of a person is what? Going to be maybe like 150? Well, no, clearly not 150. That actually is what they were. So we'll do 100 up to 250, all right, which is pretty large. And then we'll do num equals, let's do 100. And then when we say PDF of that, what it's going to do is spit out how likely it is at all those different values. And now what we can do is we can say, we'll call these PDFs or something like that. And we do plot.plot. So in PyPlot, what we're going to do is we're going to plot the X's and the PDFs in the PDF here. I'll call this PDF. I don't like the name PDF. There we go. And that's what it would look like. So in this population here, for this one sample population, this is what their distribution looks like. Now, what we can do is we can toss this in a for loop. We can say for I in range of, say, 100. So out of these, we did 10,000 samples, but let's just plot the first 100 of them, and we'll see what this corresponds to. And then I think we have to specify that they're blue, and let's put an alpha there of 0.4 or something. Maybe that'll look nice. We'll see. Oh, because I'm not plotting, I'm always plotting 0 here, right? We want to take the ith sample. So that way we're going to first plot this pair, and then we'll plot this pair, and then we'll plot this pair, and so forth. And what this will show us is what kind of populations we think are possible. Wow, that does not look very good. We should probably cap out the height of it. Unfortunately, the heights can sometimes, if the standard deviation is really low, then the height can get really high because it has to integrate up to 1. So we'll accept that some of it's going to go off the screen, and we'll specify the plot range if I can remember how to even do that. Oh boy, I have to remember how to even do this. Let's see here. Hopefully there's an example in the document here that shows it. It shows I'm terrible with Matplotlib. I'm bad at it every single time I try to use it. It's always a disaster for me. But I can never remember how to do things right in it. Oh dear, I don't see it here. We can quickly Google it. Here, let's do that. Matplotlib sets axes limits or something like that, right? Let's see here. Setting the y-axis limit in Matplotlib. That should be simple. Let's hear, Stack Overflow is always your best friend here. Plot.ylim. Here we go. That should work. All right. Or we can do it that way. There's a lot of different ways to do it, apparently. All right, this is a silly version. Get current axes. Oh, that's nice. Let's see if we can do it, though. Plot.ylim. And I believe we can just say something like 0, comma, let's go up to like 0.05. Does that work? Let's see. Yeah, there we go. Wow, that thing looks ugly. That's why he doesn't do it in the book, huh? Let's do just 10 of them. Let's just do 10 of these and see what it looks like. Maybe we can still make things out. There we go. So with 10, we can see that there's some that are centered on, say, 140 and have a wide variation. Some of them are centered on, say, 150. So this actually looks kind of what it probably does look like in reality. And all these, before we even looked at the data, we said all these are possible. All right, let's do 20 of them just to see. There we go. And some of them are like over here where it's like, oh yeah, they're all between this little tiny height right here. A little bit ridiculous, right? But you can see how it works. All right. And we can up this number here to make that look a little bit smoother, huh? There we go. Right. So this is just showing before we saw any data, what were the possible distributions for the height in the population. Now, real fast, let's replot it with the, and as long as this covers what you are interested in, it doesn't go way off into the deep end like we saw when we set this to be 100, and it was saying like 20% of people we expect to be like, you know, taller than the highest person, tallest person ever, or shorter than 0, right? Which this one does. You know, it keeps things within the realm of reasonableness, which is all that we were trying to do. All right. But now let's see what it looks like in the posterior, because now actually we still have, now let's go back here. We have our posterior all the way up here, which is this trace m height of theta is the posterior. So let's try doing that real fast. Let's take a look at that. So let's copy this. And then instead of using prior thetas, what we'll use is, what I call this, like trace m height of theta, right? And then trace m height of sigma, right? So now we have our posterior. This is after we saw the data, and that's what we think after we've seen the data. So before the data, we're like, anything goes. After we see the data, we're pretty sure on what the distribution is. It looks approximately like this, right? That looks pretty cool, right? I think that looks pretty good, actually. I'm like, hey, that's not too bad. You know, we have a good idea on what it's at, but we aren't quite sure exactly, right? It could be a little bit of a peakier distribution, right? Where they don't have quite as much spread, or they could have a little bit more spread, and it could be a little bit to the right, it could be a little bit to the left. We aren't 100% sure, all right? But that looks pretty cool, all right? So there's that, and I think that's kind of a decent place to stop when it comes to the when it comes to this basic model of just trying to figure out the height. All right. So keep in mind now, this is the distribution of heights within the population. All right. Just 1 second here. Actually, before we go on, let me specify that one more time. This is the distribution of heights in the population. Right. So we expect their typical heights to be between 140 and about 170. All right. But what was the question that we originally were interested in? What is the average height of the population? And with that, we have a lot more certainty, right? We can see right here, the average height is definitely between this small range right here. And to show that, what we can do is that we can do a az.plot KDE of this trace m height of theta. So this is our distribution for what we think the average height is. And you can see here, we think it's somewhere between around 154 and about 155 and something, right? So we got it within about a centimeter. We're pretty sure about it. And one way that we can do this is, of course, instead of the plot KDE, we can also do the HDMI. Not HDMI, the HDI. There we go. Right, so that we're 89%. So our 89% compatibility region is between 154 and 155.2. Right, pretty cool. Pretty cool. And I believe there's also, in case you're interested, I think you can just say az.summary and you just pass in the trace by itself without anything else. And az.summary, oh, no, you cannot. That you cannot do. Let me see here. I must have made a small mistake here. Installed version of RViz requires PyMC greater than 3.8. Okay, so one little issue here. It looks like this is on me, which is that ultimately I'll fix this before the next lecture. It looks like the version that they have on PyMC3 on Google Colab is a little bit out of date. So if you instead add an extra line here to install the most recent version, you might be able to get a little bit more functionality out of RViz. They usually are like in like an arms race to keep up to date with one another. And so if you have one version that's more up to date than the other, they don't always play perfectly well together. All right. Just the reality of the situation. So we can ignore this. But what this will do once you actually get it working, you can look at it. I think they do it in the examples that they have. Let me see. Yeah, so here they have az.summary, you see. Oh, I guess they do some extra stuff in there. Oh no, that is for not the posterior. I think this is still the prior. Let me take a look at this real fast here. They get the posterior. Maybe they don't do it. Maybe I was just making things up. All right, I'm pretty sure you can do a summary. Yeah, here we go. We do summary right here. And unfortunately, to take the summary of the trace, it looks like you got to get a slightly more up-to-date version of PyMC3. But if you did, this is what we'd see. We would tell you, here's your mean, here's your standard, here's your HDI, here's the standard deviation for this estimate of mu, and here's the estimate for sigma standard deviation, and there's the HDI. All right. So you would get that if we had the most up-to-date version, but we don't. So unfortunately, like I said, I'll try to fix that by the next one. If you also want, though, you can also do the AZ dot, but let me put in the HDI again in there, though. Trace M height. So at least we have that in there. So the 89% is in between there. All right, so that does it for this kind of basic. This is just a standard estimate the mean, right? And so, for example, if you wanted to do, if you were trying to do this in classical statistics, you would typically run a t-test and you say, okay, is at least this value or whatnot. Here we just say, here's our range for the mean. We're 95% sure it's between this, or at least not 95% sure, but that these values are within the 95% compatibility interval for our value here, and for our with our model, 95% compatibility interval. All right. Because once again, we aren't really sure of it because we could have some mistakes in our model. Like, for example, we assume some things were normally distributed. Maybe they aren't, right? And then we'd be in trouble. Maybe what's happening is that I'm trying to think on, oh dear. The light just went out here. I've been having issues with the with this stupid give me 1 second. I gotta somehow turn the light back on. This is gonna make for great YouTube. I'm not gonna trim this out, obviously, if you're watching this. I just gotta get the light to turn back on, and unfortunately, it seems to not want to sometimes. There's like the what it is that there's a sensor in this room that determines whether or not to turn the light on, like a motion sensor. And I think it's gotten to be the point where it is no longer reliable and needs to get replaced. There it goes. So even though I'm moving around, it sometimes turns off on me. So anyway, back back to business here. Let's finish this up since we're already at an hour and a half almost. So for the next half an hour, I'm just going to quickly do some linear regression, okay? And we'll get more practice with it in class. So let's go back to the board here and say, how do we do a linear regression? So here, suppose that now what we're interested in is something a little bit different, all right? So we start off with the question. We don't necessarily start off with parameters right off the bat here, but we might start off with a question like, how does height relate with weight? Right? That's a simple question. All right. And now we have to turn this in to a model. All right. Somehow turn it into some mathematical formulation. And a classic one, and as he describes in the book, is kind of what we would call what he calls a geocentric model, is the linear regression, which all it does is it's just interested in saying, okay, those with, for example, higher weight, do the people with the higher weight tend to have a higher height? You know, or is it that, and by how much, right? On average, if you add an extra couple kilograms, right? Sorry, let me phrase it. On average, those that are, say, a couple kilograms heavier, how much taller are they on average, right? That's a simple question that you can ask. Now, you have to be very careful in how you word these type of linear regression slopes, because it's not necessarily that the more weight causes you to be taller. It's not like you can turn to a person and say, if you put on a few pounds, you'll get taller. Of course not, right? So you can't just say if you weigh more, you're taller. Now you might say if you're taller, you may weigh more, but we're just interested in the correlation here, so we're actually doing it the opposite way, and that's a little bit unnatural. But I think in chapter like 16, he comes back and does it a different way, and I think it's pretty cool. And we'll cover that at some point, probably near the end of the course. We'll do this. We'll come back to this model all the way at the end, and we'll redo it where we actually let height affect weight, and we'll show how you can actually build a kind of cool model with it. But anyway, the point though is that a linear regression is a way of just trying to figure out how much one value changes in the population as another value changes in the population, right? So those who are heavier, how much taller are they? Those who are lighter, how much shorter are they? Or vice versa. I mean, we kind of know already that the heavier people will probably tend to be taller, not the other way. It's not like, oh, the heavier the person, it's like saying, okay, if you have a person who weighs 150 pounds and a person who weighs 200 pounds, we'd probably bet the 200-pound person is taller, right? They might not be, but on average, we'd probably guess they are. So we have that. So let's try to actually build a model out of it. So what happens here is that the model is not going to be all that different. All right, not going to be super different. The main thing that's going to change here is that I'm going to start switch. I think I'm going to switch over to mu here because this is a little bit more standard for a mu. For mu, the height for the person I is no longer just going to be some value centered on some standard deviation, right? Because now we are saying that somebody who is heavier, we expect to have a taller average height. And so now this height, this mu parameter here, isn't the same for everyone. Everybody has a different expected height, which depends upon their weight. And so now we have a mu I there. All right, indicating that now each person has a specific height that we think they're going to be centered around, right, with some normal distribution. What is that? Well, now mu I is going to be equal to an alpha plus beta x, we'll do wi, we'll say. Right? Well, what this says is, and I'm actually going to change it a little, I'll change it around just a little bit in just a moment. This is kind of the traditional way you write it. We're going to write it a little bit differently in just a moment. We're going to write it like that, but I'll show you in a minute on why. All right? It'll make sense in a moment. So what's happening here is that notice that this is an equal sign, not a distribution. Because in theory, we could write it out like this: that they're going to be normally distributed about some alpha plus beta wi, comma sigma. Right? We could write it like this, where we have some value for alpha, which is our intercept, right? Because what we ultimately are going to have is some line here, and this right here is alpha, and then our slope here is going to be our beta. Right? And every one we move over in kilograms, this is how much taller we expect somebody of that one kilogram heavier to be in height, right? So this is where we expect to be centered around, and then we expect their data to be distributed about that. That's what we expect here. And sorry, just 1 second here. All right, good. So we're still going to have to put priors on our alpha and our beta and our sigma, because now we have these 3 parameters. But what's kind of traditional is that when you're writing these models, sometimes the stuff inside of here starts getting to be very big. So what we do is we just split this out. We name it mu I, and then we just say it's the same thing as alpha plus beta wi. So it's not talking about a new distribution or anything. It's just, this is just a simple like variable name that we're using, like a placeholder value, right? And in theory, we could just take this and plop it right in there. All right. And so anyway, we have this, and now we just need to put our priors on our mu and our beta. All right, or on our alpha and beta, I mean, and also our sigma. Right. Now for the sigma, you could use a that one same uniform 0 to 50, but traditionally you instead he finally switched over to a little bit more usual normal one that people use, and I think he uses an exponential one. Exponential with lambda 1 equal to 1. And this distribution, in case you're not familiar, it looks kind of like this, but it has a pretty fat tail. So it says, okay, we expect it to be fairly small, like on average only like 1, but it readily allows for stuff like 100 without a problem. So this is considered a pretty weak prior to put on something, because it allows for it to take mostly like any value that just happens to be appropriate. All right. So anyway, now with these two though, and once again, because this is a parameter that we're not that interested in, you can usually get away with using a very weak prior on them, and it's not that, it doesn't change your results very much if you make it a little bit stronger. All right. Um, so anyway, so we're back here now, and we got to figure out this alpha and beta business. So the slope we can probably do okay with, right? We probably know, for example, that it's probably going to be positive, right? Because it's doubtful that there's a negative slope here. And then for the alpha, though, that's a little bit tricky. That one's tricky. Let's quickly draw it and try to see why that is. So let's suppose that we got some data over here, right? And that is increasing. Now, one of our beta might be guesses might look like this, and another one might look like this, right? And when you do that, the problem is that the intercept, this alpha here, it can be some really big number, it could be some really small number. And in fact, it could even end up going like way negative. So how on earth do you put a prior on that? It depends on what the slope is. If the slope is very high, we're going to end up with a very negative alpha. And if the slope is very shallow, we're going to end up with a very high alpha, very negative or very high. And so what some people actually do, and I don't recommend this, right, is they essentially say, oh yeah, this thing's like normal, zero, and like, 1,000 or something, some really big thing, because we know it could range depending on what the beta ends up being. And if the beta was somehow negative, the slope was somehow negative, then it gets even bigger. And that's the problem. It can take a huge amount of different values. And so some people would assign some really weak prior on it, and it's not a good idea because we can do better. What we do is we shift everything. And by the way, I want to just focus on this real fast, right? Why is it that alpha is the intercept? I mean, hopefully you know your slope intercept form. But the reason why is because if you set w, the weight, to zero, this whole term, this zero times beta, go away, and now your expected average height is just alpha, right? And the other problem with it is that it doesn't even mean anything, because what it means when you try to interpret alpha, it's the average height when a person's weight is zero. But of course, it's kind of meaningless, right? I suppose their average height should be zero, I guess, but it doesn't really mean anything in the context of a linear regression, because in reality, we know that a person's height kind of grows fast. They hit puberty or something like that, right? And so if we tried to fit a line on just the adult heights, right here, it'll naturally extrapolate to some unreasonable value anyway. It's not going to go to zero. If you try to force it to go to zero, that's just going to make you fit the adult heights really terribly. And so we don't want to try to force it to zero because we have some theory that says it should be zero, because we actually don't in this case, right? Because this linear regression isn't actually a real model for how people's heights change. Um, there's every reason to suspect that it doesn't actually intersect with zero. Right here at the origin. Um, so what you do, though, one thing that you can do, which makes a lot more sense, is to change it to look like this, where you say that it's beta times weight I minus the average weight in the data sample. Now, what does this mean? This is a little bit more interesting, because now, when does this term go to zero, right? Because if we want to interpret this alpha, when does this term go to zero? Well, now it is when this person's weight is equal to the average weight in the population or in the sample, right? So now what we say is that when the person is of average height, this term goes to zero and their expected height is just equal to alpha. So now we've shifted it. So now instead of alpha being where it intersects when the weight is equal to zero, it's now what we expect the average height to be when the weight is equal to the average weight, right? So here, if we have this here, we go, okay, what's the average weight? Well, it's right here. And so our alpha is where we expect the average height to be in the case of the person being the average weight. And that we can figure out, because that should just be the average height, right? The person whose average weight is probably going to be the average height, right? They're perfectly average. So now we can go back to this and we go, aha, we already had a prior on what the average height was, what the height was for the average person. That was just our 178 and 20, and we can just stick with that. So now what we've done is, just by shifting and centering the data, by subtracting off the mean, wait, we've now given this alpha, this intercept, a meaningful interpretation, which is once again the average height of the person of a person who's the average weight. And now when you do this, we can easily interpret the alpha. It's now something valuable rather than being something that was garbage like it was before, right? And so that's really cool. Just by doing this, by trying to put a prior on it and not being able to, it told us that we probably weren't really we weren't really dealing with something that was actually interesting or useful, and that we were probably handling in a bad way. And oftentimes when you have problems putting a prior on things, it's an indication that you might want to transform some variables around to actually be able to give it more meaning, something where you actually think through what you expect it to be. And so that's a really cool example there. Now for the beta, I don't know what we're gonna do. Let's just start off with some normal 0, 10, let's say, right? Centered on 0, plus or minus 10. I don't know what a reasonable value is. This is supposed to be, I think, in kilograms, and this is in centimeters. And for me personally, I don't know the conversion between kilograms and centimeters that well, to be honest, compared to pounds and height. So let's just put down a guess here, and we'll try plotting it some and plotting our priors and see what happens. All right. Man, this is a long lecture, huh? It's already an hour and 40 minutes in. We have to stop in probably the next 20 minutes or so. All right, maybe I'll go on for a half an hour. We'll see. I'm betting my earbuds are going to be dying soon. All right, so let's now do a linear regression. Let me add a little thing here. Linear regression. So that way, there we go. Now we've put it off into its own section. So let's try to plot this. So what we said was that our alphas, let's draw from our priors. All right, so alphas are going to be, let me scroll down on this thing. Oh, I haven't switched here. Here we go. Sorry. Linear regression, alphas, luckily I caught it before it was too late, are going to be normally distributed. So we're going to draw some norms from it. We're just going to do our prior simulation to see how reasonable this is. RVs of, let's see here. We say loc equals 178. Scale equals 20, and then we'll grab size of 1,000 or 10,000. Doesn't, we can just do 1,000. That'll be fine. Betas, technically these are our priors, but doesn't matter. Norm.rvs, loc equals 0, scale equals 10, and then size equals 1,000 also. And then our sigma is an exponential. The sigma actually here won't matter, because all I'm going to show you first of all is just what lines we're considering here. All right. And then we also need to get what the average weight is real fast, right? So the average weight, we can just say df2 dot weight dot mean, and then we'll call this w bar, all right, or w mean, we'll call it, all right. So first of all, what was the mean weight of somebody? 45 kilograms, right? 45. That's about times 2, 2.2, I think, in pounds. That is, wow, only 99, only 100 pounds. That can't be right. Huh? Guys are skinny. They're skin and bones. Well, I guess they're only 5 feet tall. Yeah, that's why. Man, they're skin and bones though. All right. Well, anyway, sorry, that just took me aback. All right. So let's actually plot these alphas and betas real fast. All right. So they correspond to a line here, right? So what we'll do is we'll say weights are equal to, what we'll do is we'll simulate some weights by doing np.linspace of, let's say, between, since we know, let's say 30 to say 70 or something like that. And then we have to do, now we want to plot the line. So let's first just plot the first one, which will be plot.plot. We're going to plot it for all the weights for this between 30 and 70. And the line is going to be alphas of 0 in this case, plus betas, we're just going to plot the first line right now, times weights minus W mean. All right, and when we plot this, this is what it looks like. Somebody who is 300 centimeters tall. That's pretty tall, right? Don't we say what the tallest person ever was 270? So like we should maybe add like a little line here showing this is the highest possible, and 0. Anything below 100 is pretty unreasonable. And by the time they weigh 70, they're now at negative 100. So that's a pretty stupid line already. Uh, but so be it. Maybe we should make this only be like maybe a smaller scale there. We'll do that in a moment. Let's plot a few of these lines though first, okay? What we'll do is we will plot, we'll do a for loop, I in range of, let's do 30 of them. How about? Let's plot 30 lines here from our prior. Oh, and let me specify the color here so that way they don't all look stupid. There we go. Let me also, just for the sake of argument, those are what the lines look like, but let's also do alpha equals 0.2 or something like that. Sorry, they aren't quite as ugly. There we go. So a little spindle of lines here. So our prior, first of all, you'll notice though, what is it? Right around the mean weight, right here, here's the mean weight. We already say that they have to go through 178 with standard deviation 20. So you know they're actually in the ballpark of 178 there. But outside of that range, they're going every which way, right? Some of them are going up over 600 centimeters. How tall is that? That's 6 meters. So that's something like 18 feet tall, and down to like, or so if you're heavy side, you're 18 feet tall. If you're light, you're negative in height, right? Kind of a ridiculous set of things here. So clearly our standard deviation for our slope is just way too large. So we can start off by changing that to maybe be like a 1 here. This is at least a little bit more reasonable, right? So we could do this. This one seems to me, this one feels a lot more reasonable already, right? And that's why what I was saying is that you got to actually plot this, because this is also, keep in mind, the average person. So what this is saying is that it's possible that the average person, when they're only weighing 30 kilograms, which is like 70 pounds or so, is about what is that, like, I don't know, like 4 feet something, right? No, this one's actually kind of tall, right? This is actually like 5'10", which is kind of ridiculous. But if we look at this one down here, for example, they're like, okay, they're 4 feet when they're 30 kilograms, and when they're all the way up at 70 kilograms, they're up at around like a little over 6 feet, right? So like that looks like a reasonable, plausible line at least, right? And there's a lot more in here that are more shallow that do about the same thing, right? So I mean, so it allows for a lot of variation. First of all, though, you can say, we know it's not going to be negative, right? And so one thing that he does in the book is, rather than using a normal distribution, he uses a log normal, which a log normal I don't actually know how to do in. Let me look that up in SciPy. Log normal. Uh, a log. So it is log norm. I wonder. And didn't I say log norm? Well, what's your problem? Oh, it requires an S parameter. Ooh, I do not know this distribution well at all. Probably shouldn't be messing with it, to be honest with you. But it's okay. What it does, though, is it just makes it so that way it's always positive, and it actually allows for a little bit of larger ones. I should probably, oh boy, should we try to do it? Let's see here. What is S here? S is the variance. So let's try plugging in a 1 on it and just take a look. We'll just look at the distribution and hope that it works here. What's it look like? Let's take a look at these, see if they look reasonable. I mean, they don't look out of the question. You can see that they're all have to be positive. It still allows for some of these really large ones. With this one, we could probably drop down the scale some. I kind of just made up a distribution. I think that he might have set his to be something like point. Log of B is D norm 1. I'm just looking at it in the book real fast. I think he might have used, I don't know what he used for his log normal. It doesn't really matter. He was really obsessed with making sure it was positive. Uh, Whatever. You can do it this way if you want. I'll just stick with the norm just for the sake of it, but you can make decent ones. I think in the book you can see, if you look in the book, you'll see that he has a. It looks approximately like this. I think he uses a few more spindles. Maybe he does like 100-ish. And you see, yeah, this is right in line with what you'll see in the book, right? Where it allows for some of the heights to go from like 100 up over 200, over the range of the weights that we end up seeing. By the way, what are the range of weights we end up seeing? Is 30 to 70 actually even reasonable? In the book, he plots it from around 30 to 60 something. So I think we could always just say df2.weight.max, I'm sure, is a function. So the highest that are actually in the population is around 63. What does that translate to, by the way? 63 kilograms in pounds. So the tallest person out of the 300 were 140 pounds. Wow, those guys are tiny. They're little dudes. Anyway, man, I can't get over this. Just so tiny. All right. I mean, once you actually start putting this in numbers, it's like the tallest person out of the 350 person village that were sampled. And of adults, 350 adults. That's like, if you like look at like a high school or something, like all the whole population, depending on how big your high school, it's like the biggest guy was 140 pounds. That's crazy. How tall was the tallest person? Now you're kind of. I know. I'm like almost 2 hours in. I'm going. Oh, what's the tallest person in this data set? Sorry. Max. Let's see. It's 179. That's about 5'10" was the tallest. What about the men? Let's see this. And this is of adults, people over 18. 136. 136 centimeters in inches. That was 4'5". And how light were they? This is of adults. Of adults. 31 kilograms. See that one? 31 kilograms in pounds. 68 pounds. Adult. Adult. Wow. Alright, well, anyway. Puts a lot into perspective there, doesn't it? So, anyway, now you made me want to look up the coon people. Where are these guys? Let's see here. Now I'm actually curious here. One of the sand peoples who live mostly in the western edge of the Kalahari Desert, which is in the savannah of southern Africa. So northern Namibia, I'm sorry, and southern Angola and Botswana. Yeah, so they're in the Botswana region. Wow. And they were hunting and gathering for subsistence up until the 1970s. Hmm. Wow. Well, anyway, there's a little fun thing. If you're interested in this stuff, I'm sure Hilly Kaplan. I mean, he mostly deals with I don't know if you guys know him. He's the anthropologist who works in Bolivia right now, but he has some great stories to tell because he went back for like his PhD. He was an anthropologist, and he went and lived among a hunter-gatherer tribes in South America, in like the Amazon. And he would just spend like months just like embedded in with them. Shortly after, and when like they pretty much had made like very little contact with humanity, not humanity, but the rest of civilization, I guess, at the time. And so they were just like living hunter gatherer, and I'd go in there and he'd talk to them about their culture and things like that, and learned all about them. And so it's really kind of cool stuff when you learn about some of this stuff, all their traditions and things like that. It's really really neat stuff. Anyway, and he's here in the ESI department. Although right now he's doing work in Bolivia, so I don't know how available he is. But if you get a chance to actually talk to him, it's really fun to listen to some of his stories. So anyway, back to from the Coon people. Let's go on here. Um, so this is a reasonable set of priors here, right? These are pretty reasonable priors, right? The things that we started with were not that good. So we now have switched based on doing some simulations. We found out that this was a pretty garbage prior. And instead we're going to do some log normal 0, 1, or at least I think that's about what we have in there. All right. I'd have to look up a little bit more about the distribution, how it's written in NumPy or SciPy to know for sure. But this gives us a gist of what we have. So now what we're going to do is go and actually fit this line using PyMC3, right? Actually fit this to the data. So what we do is just like before, in fact, one of the great things is that once you write one of these once, you can always just copy and paste it if we really want. Oops. Right. Now we're going to do a model, and I'll call this like lin for linear. I just want it to be a little bit short. And same thing here, I'm just going to call this trace lin just to make it shorter because I hated typing that whole thing out. So let's see here. So now we have, instead of theta, we have our alpha and our beta. And the beta was a log normal. Do they have that in here? Ooh, I do not see log normal in here. And oh, it would be a capital, that's why. Log normal right there. Mu is equal to 0. Sigma should be 1. All right. And then this one is our alpha, and I got to name this too. This has to be named beta. Right. So alpha is still centered 178 with 20. The sigma, we've switched this now to be an exponential, which I like a lot more. I'm a lot more comfortable with this one than what he was doing. It just gave me the heebie-jeebies when he was doing the when he did it with the uniform there. That one I just don't like that one. But anyway, it's okay. And then the exponential, the lambda is equal to 1. We'll talk more about the exponential in class today. I mean, because we didn't quite get to that Uber problem. In the Uber problem, we have an exponential a lot, and so we might try getting to that in class on depending upon whether or not we have time. We'll see. It's a pretty cool problem. So anyway, so here we go, and what we can do is that we can directly say that the height should be centered on, and then we could pass in the formula for the line right there, or we can say the mu's, the average heights that we expect are going to be alpha plus beta times df2 dot weight. Oh, not weight. Don't forget we centered it, so we have to subtract off w bar, or what I call it w mean, I think. There we go. So how far above or below the mean weight they are, right? And so those are our mu's, and now we can just pass that in. So now each one of them, now this is a list of mu's, right? One for each person. They get their own specialized mu according to the line, so that way they fall in the line. And their height should be centered on that with some standard deviation sigma. All right. So now we can run that and get our trace samples. All right. And we'll take a look at what happens with that. This should be fun. All right. Now, one thing that's interesting is, let me go back up here real fast. We had estimated our HDI for sigma, didn't we? Did we estimate our HDI for sigma above here? Let's take a look real fast. It's important to think about this now. The HDI for sigma was between 7 and a little lower, like 7.3 and 8.2. What we're going to see is that the sigma is going to be lower here, okay? And I'll show you why that is in a moment, all right? So we've sampled it. Now we can say trace, we'll do az dot, I really wish I had that nice little summary one. But so first out, so I was just talking about it. Let's take a look at the sigma before we do anything else. And you'll notice right now it's sampling sigma, beta, and alpha. All this other stuff you'll ignore. We'll talk about it once we get into chapter 8 here. But now we see that the sigma is down at 4.7 to 5.3, way lower, right? So the variance in the population from our expected mean has gone way down. And the way that you can see this is that you can imagine what we were doing before when we looked at this was we had a bunch of heights here, right? Where, okay, here's some heights of people, right? Maybe I'll use dots instead, right? And I'm just, in reality, there's nothing offset about them, right? It's like they or normally distribute about this, right? Here's all the points. And then we had to get our estimation of the mean, and then we said, okay, well, there's some decent size variance here, right? Now, what we've done is it turns out these guys who are really short, really short, they tend to be really light also. And the guys who are really heavy, they tend to be the heavier. Guys who are really tall tend to be the heavier guys. So what we've done is we've taken this data right here and we've kind of split it out. Now, sometimes you can be tall and you can be short and heavy, or you could be tall and light. Sure, it's not 100%, but in general, once we've changed this x to be a weight here, what's happening is that these guys suddenly spread out like this, right? The guys up here go this way, and the guys down here go this way because they tend to be skinnier, and these guys are way less, and these guys are way more. I'm not going to call anyone skinny or fat in this population, given that the heaviest is 140. So suddenly they turn out like this, right? And now we fit a line like this. So now we've explained a lot of the variance as being accounted for in the weight. And now when we look at how far off they are from this, now the standard deviation is much larger than where it was before, where it had to be accounting for the full population difference from the mean value. Now we've accounted for a lot of the variation. So that way, well, this guy, yeah, he's taller, but he weighs more. So he's actually more in line with what we expect. Before he looked like quite the outlier, right? Or at least that there was a lot of variation in the population. But a lot of that variation is accounted for in the weight. Because of that, the estimated standard deviation from this estimate that we have for the person has gone down a lot. And that's one indication that we're actually picking something up here. All right. So let's go here and plot this a little bit more. So then let's take a look at some of this stuff. So what we're going to do is first things first, let's plot some of the predicted lines, and we'll also plot the data too. All right. So let's see here. So I think there's pandas pd dot plotting dot. Oh boy, I have to try and remember how to do this. 1 second here. df dot plot. I think you can do. And then you can pass in the weights. I think you do something like weight and height. I think you do this and this works. Ooh, lordy. I think instead of plot, we want to do scatter. Oh no, there is no plot. Oh no. Is there a plot scatter? Oh no. Is there a scatter plot? 1 second here. Yeah, no. Plots. Alright, maybe we just have to do a like that. Does that work? Oh no. Okay, I'm in trouble here. I gotta try to remember how to do this. All right, let me see here. Pandas, plot, scatter. Plot dot scatter is what it is. I tried out like all the different combinations. There we go. There we go. There's a scatter. And of course, we want df2, because I screwed that up right there. Of the adults, this is what it looks like. And it looks surprisingly linear, doesn't it? That actually looks pretty good, huh? I'll take that. I just want to make sure I actually fit this on the adults. Yeah. This is sometimes I sit there and go, maybe I should have just renamed DF2 there. And so that way I never would have mixed them. You can see all the kids on the left side there I was going to point out. And it's decidedly not linear there, is it? Anyway, here we go. So we got this, and what we want to plot on top of it, if we can, is the line. So first we'll just plot the average estimate for the alpha and the beta, and we'll plot on top of it. So let's do that. So we'll say plot dot plot. We still have our sample weights up above here. What do we call it? We call it just weights. Perfect. So we'll plot weights against, and now we need to actually have the mean alpha and the mean beta, right? So we'll call this alpha bar is equal to our alpha mean, depending on what you want to call it there, is equal to the trace ln of alpha, and we'll just say np dot mean of that, right? no, that didn't work at all. So annoyed by this machine sometimes. Anyway, let's hear. Beta mean beta. All right, so we got our alpha and beta, and now what we want to plot here is alpha mean plus beta mean times the weights minus W mean, right? That's our line of best fit. So when we plot it, there it is. Let's give it a color here. I think we can do like K. Is that black? Yeah, there we go. So there we go. That's our line of best fit. It looks pretty good, right? Looks pretty good. All right. But we want to capture some of the uncertainty in here too, right? We got to capture the uncertainty. It's not acceptable to ignore uncertainty here. So how do we do that? Right? That's a good question. So what we have here, because, you got to keep in mind here, we don't just have one line. This is the nice mean here, but we have more than one line, right? We don't know for sure what the alpha and the beta actually are. They have we have samples of a bunch of different possible ones. Sure, the mean might be one of our best guesses, but we have a lot of different ones. So let's actually try plotting them instead. So I'll keep that mean one on there just for effect. But let's actually plot a whole bunch of them. So what we're going to do here is we're going to say for I in range of, let's just plot 20 of them, let's say. Oops. Let's do 10. 20 is probably fine. This is going to be a crowded plot. Let's do 10. And what we're going to do here is just plot weights, and then we'll just do, instead of the alpha mean, we'll just grab the ith alpha, right? So this is trace len of alpha of I, and then beta mean is instead going to be trace len of beta of I, right? So we're going to grab our ith sample for our alpha and beta, and we plot that. Oh dear. There we go. All right, and now we get these 10 lines, and let's make that alpha be. Let's give that an alpha 0.2. Here, maybe a little bit thicker of line than that. Let's do 0.4 or something. All right. And let's also let's make these red instead, just so that way we can tell them apart from the mean, right? So here we go. This is what it looks like. That looks pretty cool. We can knock that down a little bit. We actually have a pretty tight guess onto what the line is, right? The line of best fit, we can see that definitely around the average. Remember, what was the average weight? Oh, and do you want, maybe I should knock this down to only like 65 rather than 70. Just because that was, it turned out that the average was 65. And, the max was around 65, not 70. And right now it's going a little bit farther. There we go. So when we look at the average weight, it's pretty tight. And in general, it's pretty tight overall. But once we get all the way to the very heavy ones, there's a little bit more variation there, right? It's a little bit wider of intervals, right? Some of the lines allow to go a little bit higher, and some of the lines allow for them to drop a little bit lower on that end, above the mean. So we have a little bit of uncertainty there. There's still a little bit of wiggle room in this, but we got a pretty good idea on where it is, right? One thing that you can do is you can always plot. So I always like making these little these little lines here. It looks it's a nice effect to show kind of, well, there's a lot of different possible values for it, right? And in here you see we have a pretty good tight estimate. Now, does that mean that we're very certain on this? Well, you got to keep in mind that still this is based on all of our assumptions that went into it about it actually being a line, right? So one thing that you can read is that you can interpret this as assuming that it was a line and that these things are normally distributed about that line. This is, we're pretty sure that the best fit is within this region, right? Now, just to see how much this changes, let's go back real fast and change it to be only, say, 10 data points rather than all of them. So what we're going to do is, instead of taking all the heights, we're just going to take the first 10 of them. All right, that should be fun to see. What happens if we do that? Now, obviously, we're not going to get nearly as reliable of estimate, right? So let's take a look at this. This should be a lot of fun. Oh, I shouldn't be plotting everything here. I should be plotting df2 of only the first 10. There we go. So here, if we only had 10 data points, you can see that now we are not nearly as certain about our line, right? It could be a pretty steep slope there, right? Or it could be a much more shallow one, right? And it could be up or down because we aren't even sure about what the mean is with only 10 people. But this shows you how uncertain we are about the line of best fit. While lots of times you might just be used to, oh, do the least squares and here's the line here, right? This black line is maybe all that you would have seen. Now we have a little bit more information, right? We have the full uncertainty and what it entails. And that looks pretty cool. Now, one way that you can plot this that's a little bit cleaner at times, if you're so interested, is you can do an HDI plot using RViz, which is pretty cool looking. What it will do is instead of doing like multiple lines, it'll shade the region in which it could be within 89%, or yeah, 89% here. And so the way that we do that is we just have to first calculate the well actually I'll show you. All you have to do is let me think on this. How do you do this? az.hdI plot HDI, and what you have to pass into it is you have to pass in some specific things. First of all, we want to plot it over the weights that we have, right? And then for the y, you have to say what are all the samples for each one of the weights. What are the different range of samples that you can have? And so to do that, though, we're going to have to first make a big list of them, right? So we're going to have to say our views or something like this is an empty list. And we're going to have to say for I in range of laying of trace when. So for each one of our samples, what we're going to do is add on to this the trace len of alpha of I plus trace len of beta of I times weights minus W mean. All right, so what we're going to do here is for each one of our samples, each I sample, we're going to calculate for all the weights, all the different weights from 30 up to 65 that we had that little line up for, calculate what are what the line is, right? So we're going to calculate every single line, and we're going to put them all into a list, all right, which is muse. And then what we're going to do is plot the 89% confidence region, or credible region, or sorry, the compatibility region for all those lines, and that's what we get. So to see it here, let me print the muse here. It's going to be some big mess, so we can't look at it too long. But here is for every different weight, going from the lowest weight all the way up to the tallest weight. This is the projected mean, right? That's where the line is. That's that line just going up, and that was for that specific sample of the alpha and the beta. And we do it for all the different alpha betas, all 1,000 of them. And then using that, now we can do the 89% credible region or compatibility region for each one of them. And you'll see, once again, it gets skinnier towards the middle and then fatter towards the edges. Looks pretty cool. So this shows us how uncertain we are about the line of best fit. Now, on top of that, you have additional uncertainty. And because this is already going over 2 hours, I'm going to stop it here. But one thing that you can do is you can also overlay, keep in mind that the data itself, the predicted heights of the people, they still have that sigma in there, and they're normally distributed about the line of best fit. So then what we end up having is we aren't sure about the line of best fit, and on top of that, the people's heights will vary from that line of best fit, right? And so from our alpha and beta line. And so because of that, you have pretty much uncertainty on top of uncertainty. So if you're trying to predict somebody's height and say what's a reasonable range for somebody's height when they weigh 45, well, first, you aren't even sure what your estimate of their height should be, right? But then on top of that, of what their average height is, but on top of that, you know that their heights will vary from that. And you can actually plot all that together. And so I don't have time to do it because I'm already gone well over what I anticipated. Uh, Man, they make just better plots than me. Man, I'm quite jealous. There's the HDI plot. And here it is right here, where they overlay an extra HDI plot for what the actual distribution is for the people using the sigma samples as well. All right. So I'm not going to do that right now. Like I said, I just unfortunately just don't have time given, how late this is already going. I don't want to keep you any longer. So what you can do though, what's very cool is that there is an inside of PyMC3, there is a sample. You'll see this right here, posterior predictive. And what this will do is it will actually sample the heights. It will give you sample heights for all the people in your data set. And you can pass them the trace and everything. So I'm not going to do that right now, like I said, but it's surprisingly cool, right? You can pass in, let's see here, trace, which is trace len, and then, oh, I'm not quite sure, model. So you have to pass in the model, which I think was like model height, right? And then you have to pass in what variable you actually want to get, which I think is like bar names, or maybe that alone will even work. Nope. All right, I don't remember exactly, but like I said, I'm still learning this one. But you can actually specify. You can pass in your samples for alpha and beta and sigma. Pass in the underlying model, and it'll actually generate the heights for you. For okay, well, this is what you predict, and these are some sample heights for each one of the people in your data set that you might predict for each one of your samples, and then you can plot the HDI on top of that. All right. Anyway, I'll stop it there. Read the book or watch the lectures. He'll go over some of this and some more. It's really cool stuff. And this will show you kind of just doing the basic linear regression, doing it from all this approach with the full uncertainty analysis. All right. So I'll leave it there and I'll see you guys in class.